Okay, so I mentioned potential temperature and showed a figure. We'll see how potential temperature comes about. We already said what it is. Basically, you move the air parcel to a reference pressure and see what its temperature is with respect to the reference pressure. Going back to our ideal gas law, we had P equals rho times the Rg divided by Ma. So this is a universal ideal gas constant and its particular mass. So you end up with ideal gas constant rho RT. And we have our second law of thermodynamics where we said the heat gained or lost by the parcel is going to depend on the internal energy change and the work done against the atmosphere because it's compressible. So dP is the compressibility effect, right? So R plus CV is of course Cp as we already know. So it's Cp dt minus dP over rho. We did this already from Clausius equation before, so you can look it up again. When we move a parcel adiabatically, it doesn't gain or lose heat, so the change in Q is 0. That gives us Cp dt equals dP over rho, which we already saw once. We'll do this again just to get our definition of the potential temperature. So Cp dt is RT dP over rho because we are just adding the ideal gas constant for dP and dt and so on. So Cp dt then RT dP over P, and as soon as you see this, you know that that's going to lead us to a log relation. So you can write this as dt over T, take the T over here, R over Cp, which is a constant kappa, and dP over P. So dt over T is kappa dP over P. Very simple derivation. Kappa is a constant of 2 over 7, just properties of ideal gas. So you write this in terms of log because whenever you have dt over T and dP over P, you can write them as d of ln T minus kappa d of ln P equals 0. Delta Q is 0. Or you can write this as d of T over pk equal to constant. Okay, you can convert this. You can write this as d of ln P to the k, and together you can write this d of T over pk. If it's 0, then T over pk has to be constant. Very simple math. Go and remind yourself of these simple math if you are not able to follow. So that basic thermodynamic relation, second law of thermodynamics, gives us a quantity theta, or T over P to the K is constant, but if we reference it to a pressure that is prescribed, then you can write this as a temperature because it's a temperature multiplied by a non-dimensional number. Pressure is non-dimensional. So when you move the parcel to a different pressure adiabatically, then the temperature is going to change by that ratio of R over Cp to the power, of the ratio of pressures. That's all. Why is this important? Because T over pk is T over P to the k is constant, so theta is conserved in dry processes. Okay, so going back to our equation, d ln T minus kappa d ln P equals 0, T over pk equal constant, we can write this as d theta over theta equals dt over T minus kappa dP over P, which means theta is conserved. Okay, so going back to our figure of this parcel moving from Z1 to Z2, theta of the environment at Z2, okay, don't get confused. Theta of the environment can change, obviously, because there is a lapse rate we saw. The slope of theta E is positive as opposed to the temperature, which was negative, but it's the theta of the parcel that's conserved. That's what we are after, right? So theta E of the environment at Z2 is theta of the environment at Z1 plus d theta dz, which is the lapse rate of potential temperature of the environment times delta Z, small movements. So theta 1 plus d theta dz of the environment times delta Z. And again, we can define stability now. If d theta dz of the environment is less than 0, then the partial movement is going to be unstable, but we know that it's positive. So the dry processes are obviously going to be stable, as we saw. If it is 0, if it's vertical, then, or if it's horizontal, then it is neutrally stable. And if d theta dz of the environment is greater than 0, then it's stable, and it is greater than 0, as we saw, which we'll see again. Compare that to dt dz, the temperature itself, instead of the potential temperature. It looks very similar, except temperature of the environment is not conservative to dry processes or moist processes. This is conservative to dry processes. Okay, so this is the compressible versus incompressible relation. So this would be for water. In the water which is incompressible, you can use temperature gradient and move the parcel. Pressure effect is not going to be important, whereas in an compressible fluid, we have to move the potential temperature because the pressure effect, compressibility effect, is going to be important. So let's look at the profile again. Non-conservative quantity and conservative to dry processes, dry potential temperature. We will define this in the next podcast, but this is positive, so atmosphere is nearly always stable to dry processes, as we saw with the dry convection. So what happens in this sense then? If you move air, let's say in a desert, with two different temperatures, you heat them and it's dry air, the parcel moves up. It's just going to reach its height of neutral stability, move to its height of neutral stability, and on the theta it's going to look like this. Right here it's harder because we have to move along a slope, right? Whereas if we look in the theta framework, convection is going to look like you are going to move vertically. So you're starting with T1 but theta 1, T2 but theta 2, so you're going to move to theta 1 and theta 2, move up your stable position, move up your stable position. So that's convection in the atmosphere in terms of dry potential temperature. This is why we define potential temperature, comes directly out of our convection and thermodynamics and compressibility and adiabatic movements. Fairly straightforward, but you should go through it and make sure you understood it. Okay, the expression is very simple to remember. T over pk is constant, and that most of the time that's enough, but you have to know the derivation as well, because instead of remembering, you can always go back and derive it from first principles, starting with the second law of thermodynamics, ideal gas law, etc. That's always useful to be able to do.